Okay, so let's do this Poisson regression. So let's remind ourselves about the Poisson distribution. So the idea of the Poisson distribution is you've got some independent observations. And the whole idea is, and this comes from what we call the Poisson process. So if you're not sure about this, go back to probability and statistics. But the idea is that you've got a constant rate of success, and we'll call this lambda. And basically the mean rate lambda is equal to the variance. And the whole idea is you've got, in the Poisson process, you're looking at events over time. And we know the number of events is proportional to the amount of time you look at, and non-overlapping time intervals are independent. But the other key thing to remember is that the mean rate lambda is equal to the variance lambda, because obviously we can use that to think about over dispersion like we did with logistic regression. So as always, let's motivate this with an example. And this example comes from the Zur book. And what they did is they were looking at roadkills. They were looking at amphibians, so frogs, toads, newts, and they were seeing how many got killed, and they looked at the distance from a particular national park. So we've got the distance, I believe, in, I'm going to say meters or kilometers, can't remember off the top of my head, and we've got the number of road kills per unit amount. And basically, if we plot the distance, I think that has to be meters. Yeah, because that's 25 kilometers. Yeah, let's say meters. If you plot the distance on the x-axis here from the park, and then we count the number of road kills, you can see that generally, as we get further and further away from the park, we have less road kills, which sort of makes sense because this national park is a good sort of environmental area for these amphibians to live. So how are we going to model this? So let's think about our data. We've got, in our case, our distance, x1, x2, xn, and we're going to have our number of road kills. And because we've got a count here, we've got integer amounts. When we're actually looking at this, we can't have negative numbers. We could have 0 road kills, but we can't have negative road kills. And what we want to do, if you think about it, whenever you're trying to model things that are counts, the classic way is to use the Poisson distribution. So we're going to say that our response variable yi has a Poisson distribution with a rate lambda I, and we'd like to relate this lambda I to our distance in our case. So that's what we want to do. So we're going to have some model to link this because, again, our linear combination predictors could give us any number, including negative numbers, and we sort of want to go, well, we don't want that. We only want 0 to positive numbers. So we're going to have a link function again. So how do we do this? How do we make sure our lambda I is positive? Fine, we're going to set e to I equal to log lambda I. So this is our link function. So we're going to have our eta is again going to be a linear combination of our predictors. So here we've got k predictors, or in our matrix notation, eta equals x beta. And then we go from that to something that's going to work by using our link function log. So this is actually our third example to some extent, because we started with our linear, which you're all used to, which in that case our y equals n, our mu I sigma squared. And in that one, our link function was just the direct thing. We just basically set it to beta 0 plus beta 1, etc. Then we had our binomial case, the logistic regression. We went to our general linear model, and in that case we had this, what we call logit link function. And now here's our final one. Now we've got a Poisson with link function. And in fact, any distribution from what we call the exponential family can be fit within this. So you could come along and say, well, actually, I want my response variable to have this distribution. And you can go and look up the link function and put it in the GLM. And in fact, you could use the GLM to get your linear regression if you basically go family equals Gaussian, link function equals identity. But we don't bother because we've got the linear model. So let's have a look. Here's me actually fitting it. It's a GLM. We just put our road kills. We don't have to do anything fancy response variable like we did before with successes and failures. We just go road kills. It's distance park. Here's our data. And this time we go family equals Poisson. And then we look at our summary again. You can see, we ask the question, is the distance to the park a significant predictor? Here's our p-value, very, very small. So yes, it's a significant predictor. We could always look at our residual deviance. You can see this is quite large. And in the case study, I go into this data a lot more and show you that we can actually improve our predictor a lot more. There's a lot more predictors we can put in here. This is just illustrated. So the question is, well, what does this mean, this coefficient? Well, first of all, it's negative. So as we increase the distance away by a unit, obviously the amount goes down. But how do we interpret that coefficient? Well, before we do that, let's have a look at our predicted values. Here I've done our predicted values. I'll show you in the case study how I got this graph. But you can see that our predicted average roadkills goes down as distance increases. Bit of a concern here with this sort of dip. And again, in the case study, we'll explore that. So let's interpret this coefficient. Let's think about what happens. Let's assume I've got some xi, I've got beta 0 plus beta 1 hat. And then I increase my xi by 1. So I want to say, what does this beta 0 do? So I've got my new value. And remember, we've got our log yi is this because our link function. So our log yi dash equals beta 0 and I put xi plus 1. I open this up, rearrange it, and I get this. The beta 0 plus beta 1 xi is our original log yi plus this extra beta 0. So what we're finding is our new yi is basically, if I take my coefficient and I exponentiate it, it tells me how much I can times my yi to get the new yi. So it's a multiplicative increase. So our coefficient, we take it, we exponentiate it, and that tells me how much I would multiply my y times to get the new y. Okay, let's go back to our case. So I've grabbed the coefficients from my roadkill GLM. I exponentiate the second coefficient, which is the one associated with distance, and I get 0.9999. So what does that mean? Each time I increase the distance by a kilometre, or is it a metre? Still don't know, but anyway, let's assume it's a kilometre. Every time I increase it by a kilometre, then I would times my value by 0.99, which is the equivalent of decreasing it by about 1%. Make sense? Good. So next thing we'll look at poisson regression, but that is poisson regression. As I said, go and look at the case studies. We'll look at that in much more detail. See you next time.